This video will review piecewise functions. In particular, we're going to look at how to use the graph of a piecewise function to find the equations, and then afterwards we'll look at how you can graph the piecewise function if you're given the equations. To begin, let's look at a simple definition of what a piecewise function is. A piecewise function is any function that has multiple parts or pieces. Each of these parts or pieces will have its own domain that describes when you follow each equation over what set of x's. Now let's begin by looking at a pair of graphs. In the first graph, I have two segments joined together. The two segments tell me that we're going to have to use two equations to write it. Now this piece on the left is where we're going to begin. This graph starts at the point 0, 3, and this segment ends at 2, negative 3. This tells me the domain for this segment would be from 0 to 2. Now over this interval, or over this domain, it has a slope of negative 3, and it has a y-intercept of 0, 3. Now because I know the y-intercept, I can write it in slope-intercept form. That is the form y equals mx plus b. To begin, I'm going to write the function notation f of x equals, and I could use any notation here. I could use f of x, g of x, h of x. It doesn't matter because it didn't tell me. And because it's multiple parts, I'm going to have to use the bracket here. The first one is going to be, again, using that idea that it has a y-intercept of 0, 3 and a slope of negative 3. I'm going to say that it's negative 3x plus 3. Now when I do this, I have to say the domain at which this happens. It begins at 0 and continues to where x is 2. Now at 2, it changes to the new equation. If you do not include 2 here, and we have not, that means we'll pick up 2 on the second equation. Now if for some reason that 2 was included on this piece, then we wouldn't be able to include it on the second equation. Now for the new equation, I don't have the y-intercept given to me, and I don't need it. Instead, I'll write the equation in point-slope form. Point-slope is what you do when you know any point on the line and the slope of the line. Here, we know that it's going through the point 2, negative 3, and we can look at it and say that the slope is 1/2. If we want to put this in point-slope form, this new segment would have the equation half times the quantity x minus 2 because it's after where x is 2, and then outside minus 3 because that's what the y value is for that point, the 2, negative 3. Now this interval, because we didn't include 2 before, is going to be 2 less than or equal to x and then less than 4. We can't include 4 here because 4 was an open dot. Now in the next problem, we see that we have 3 unique pieces. We have the 2 segments on the left and the ray on the right. This means I'm going to need 3 equations to describe it. Starting with this first piece, we're going to say that f of x equals, and again the bracket, or the solution set. This piece on the left begins where x is negative 4 and ends where x is negative 2. That's our domain. The domain is negative 4 to 2. There is no overlap, so we'll include both of those points in the domain. Here the slope is positive, the line is rising, it's increasing, and it's going up 2 and over 1. Now I can choose either the point negative 4, negative 1. I could also use the point negative 3, 1, or I could also use the point negative 2, 3. Again, that would be negative 4, negative 1, negative 3, 1, or negative 2, 3. Any one of those could be used in the point-slope form. Now I'm going to choose the point negative 4, negative 1. Again, it's arbitrary. I can use any of the 3 points that are clean that go through the line, or the line goes through. So if I do this in point-slope form, again, the way I got this is there's a slope of 2, and it's after the point negative 4, negative 1. The domain here is from negative 4 to negative 2, both included because we have closed points, and there's no overlap. Now the next piece is a horizontal line, and this is where the y value is always negative 2. So when you write the equation, it's just f of x equals negative 2. Here the domain is from negative 1 to 2. There's no overlap, and they're both closed points. So we'll include both negative 1 and 2 in the domain. The third piece is a ray, meaning it has an arrow that goes in one direction, meaning the segment starts at the point 4, 5 and continues forever with that same slope. Here the slope is going to be going down 4 and over 1. So when we write this one, I could use either the point 4, 5, or I could use the point 5, 1. I'm going to use the point 4, 5. If I do this, again, it's got a negative 4 slope, so we'll say it's negative 4 quantity x minus 4, and then that plus 5, indicating that the slope is negative 4, and it passes through the point 4, 5. Here the domain begins where x is 4, And the arrow tells me that it continues in this fashion, meaning it goes towards infinity. As infinity can never be achieved, it's just always going to be less than, never less than or equal. Now in the next set, we're going to start with a piecewise function like we see in the bottom right, and we're going to graph what those things look like. So in this case, I have three pieces. F of x equals -8 for the domain -9 to 5, -5 rather. And then it becomes the quantity x plus 2 squared minus 4 for the domain of -5 to 0. And then it becomes 2/3 the quantity x minus 3 minus 4 for the domain of 3 to infinity. All right, the first thing you want to do when you have any problem like this is set your graph up. So we'll do our label and scale. Looking at the first equation, the f of x equals -8, it doesn't have an x. This indicates that it's going to be a horizontal line and it's going to pass through where y is -8. Now when you graph this, you're going to go to where x is -9, so the coordinate -9, -8, and continuing to the right until you get to the point -5, -8. Now again, I know it's going to go from -9, -8 to -5, -8 because that's the domain for this first piece. Now when we get to the -5, -8, we see that it doesn't have or equal, which means we want to put an open point. And there's our first segment. Now the second one I see is the quantity x plus 2 squared minus 4. That squared indicates that we're not dealing with a line. Instead, this is a parabola. And that parabola is given to me in an equation with vertex form. Looking at the form, a quantity x minus h squared plus k, I see that the stretch is 1 and the vertex is -2, -4. And again, I probably want to list this out. If you ever see in the problem, justify your reasoning, this is what I'm doing. I'm telling you, this is what I know. The stretch is 1, and it has the vertex -2, -4. Now, if we start with that -2, -4 vertex, we go over 1 and up 1 squared, then over 2 and up 2 squared, over 3 and up 3 squared. However, you may notice that I didn't go to the right 3 and up 9. That's because my domain is limited. My domain is the pieces from -5 to 0. This only gives me a piece of the parabola. Connecting it, I get this nice U shape. Now the last piece has the form -2/3 x minus 3, or positive 2/3 times the quantity x minus 3 minus 4. This is a line and this is given in point slope form. Here I can see that the slope is 2/3 and the point would be 3, -4. For this problem, the domain goes from 3 to infinity. So 3, -4 is the beginning of this line because the domain starts at 3. So the slope is 2/3 and it goes through the point 3, -4. Again, I want to write that. That's the justification for my reasoning. Plotting the points, I'll start at 3, -4 because that is the beginning of my domain. And I'm going to continue this towards infinity. Now I've drawn it once. I could draw it again. And the way I would do the next set of points would be to go again up 2 and over 3. Because this approaches infinity, it will have an arrow going to the right. So when I draw this, I'm going to draw that arrow going to the right. And there's my 3 pieces of the graph. We had 3 equations. We should have 3 pieces to the graph. All right, I hope this problem helps you to understand piecewise functions. Thank you for watching.